Okay. Good evening, everybody. So let's get started. So yesterday we were looking at the convergence analysis of the secant method, right? We were kind of halfway through. We didn't finish it quite yet. So we defined En plus 1, that is the error at n plus 1th iteration as r minus xn plus 1. In general, we define error to be equal to the root minus the solution that is obtained, right? So En equals r minus xn. Similarly, En minus 1 would be r minus xn minus 1 and so on. Then once we have En plus 1, we have the definition for a secant method, that is the new iterate xn plus 1 is basically going to be xn minus f of xn divided by f prime xn. But then, unlike in the Newton method, we have f prime xn is replaced with this finite difference value, that is basically the secant slope of the secant, right? And that is what we have written, a new value for xn plus 1. Now, if you're going to substitute for this xn plus 1 in here and then going to simplify, then you're going to get and then do a little bit of algebra by multiplying and dividing with xn minus 1, essentially this quantity. Then you're going to get for this En plus 1 as xn minus 1 divided by f of xn minus 1 times. We also will get this f of xn by En minus f of xn minus 1 by En minus 1 divided by, you get this xn minus 1, which is basically multiplied and divided, and then you get a product of En times En minus 1. So what we said yesterday was we were able to define now En plus 1, the error at the n plus 1th iteration as some factor times En times En minus 1, right? Now this factor also contains En minus 1 and so on. So there are several things here. So we need to see what is this factor and then simplify this factor, and then we will then be able to talk about how does the error as n plus 1th iteration go as a function of En, right? That is what we are interested in eventually. But then because this method it requires 2 steps, right? It requires 2 steps. That means you want to calculate n plus 1. It requires data from n and n minus 1. So as a result, the error at n plus 1 is now in terms of both error at n and error at n minus 1. Okay, that's what we have obtained. Okay, now let us take a look at these things. So I want to obtain an expression for what is there in this square bracket here. So for that, let me look at what is f of xn, right? I want to actually calculate what is this quantity. Okay, I want to calculate this quantity and then see. So for that, let me write what is f of xn. I want to start with this thing. F of xn equals essentially f of r minus En, right? We have defined En equals r minus xn. That means xn equals r minus En. Then I can use Taylor series expansion and write this as f of r minus En times f prime of r plus En square by 2 factorial times f double prime of r minus and so on, right? That's what we will get using Taylor series expansion. Then what is f of r? F of r is basically function value at the root is basically 0, right? Because that's what we are interested in. And essentially that means f of xn equals minus En f prime r plus En square by 2 f double prime r n plus and so on. Okay, I have obtained this thing then, but what we want is we want f of xn by En, right? That is what I want. So I'm going to divide this entire equation with En, or bring En to the left hand side. This is going to be f of xn divided by En equals minus f prime r plus En square by 2 will become En by 2 f double prime r plus and so on. Okay, that's what I have got. Now, of course, I can repeat the same process, whatever I have done with this f of xn, considering f of xn minus 1. I can also write this as f of r minus En minus 1 and expand this in Taylor series. Okay, and proceed and so on. Eventually, I'm going to end up with similar looking equation, but then instead of xn En, instead of n, I'm going to get n minus 1. That's the only change that's going to happen. So I'm simply copying, I'm simply writing this equation, okay, with n replaced with n minus 1. So this is going to be f x sub n minus 1 divided by E sub n minus 1 equals minus f prime r plus En minus 1 by 2 f double prime r plus and so on. Okay, that's what we obtain. Now I have, let us say, let's call this equation 1, let's call this equation 2. I'm also kind of not interested in the other higher order terms here. We are going to truncate it at f double prime r term. Okay, then what we want from our expression is we want f of xn by en minus f of xn minus 1 by en minus 1. That's what we want. So that means this is going to be these two expressions, 1 and 2. I have to subtract 2 from 1. So that means 1 minus 2 is going to give me f of xn by en minus f of xn minus 1 by en minus 1. That is going to be minus f prime r plus f prime r. This is going to be 0. Then here I'm going to get en minus 1 by 2. That means I'm going to get 1 by 2 f double prime r times e sub n minus 1. Okay, that's what I got. Fine. So that is what I obtained. But then what I have is I have this ratio f of xn by en minus f of xn minus by en minus 1 divided by xn minus 1 divided by xn minus 1. But then I know that xn minus 1 equals because my r equals e equals r minus xn. I can write xn as r minus en, right? That's what I can do. So I'll go back and write here xn as r minus en minus r minus en minus 1. So that's going to give me the r gets cancelled with this r. Then I'm going to end up with en minus 1 minus en, right? That means if I were to write, that means xn minus 1 is nothing but equal to xn minus 1 is equal to minus of en minus 1, right? That's what it is. That means if I were to just take this term f of xn by en minus f of xn minus 1 by en minus 1 and divided this with xn minus 1, that's what I'm interested in, right? From the previous value here, right? That's what I'm interested in. So that can be written as, if I want to substitute for this term, if I'm going to, for this term, I'm going to substitute from here. But then I realize that my xn minus 1 is actually minus en minus 1. So that's going to be, if I'm going to substitute for these two, I'm going to get 1 by 2 f double prime r times en minus 1. That is for the numerator. Denominator, we have minus en minus 1. So again, this is going to get cancelled with this. And then I'm going to end up with essentially minus 1 by 2 f double prime r. Okay, so that is what my this factor is, right? Okay, where is the factor? I think it's still above. So it is this factor. This factor is what I got as minus 1 by 2 f double prime r. Now, what about this term? This is, so that means I have another term. So the other term is xn minus 1 divided by f of xn minus f of xn minus 1. This is nothing but in the vicinity or in the vicinity of the root, right? This is nothing but approximately this is f prime r, right? Of course, this is 1 by f prime r, because if you take function value divided by the distance, that's going to be f prime r. So this is going to be approximately f prime r, because we get very close to the root. Okay, so that means this is equal to the slope of the root. That means I have now expressions for both these terms, right? This is the term 1, this is the term 2, right? T1 and T2, which are actually being multiplied in the expression we have derived earlier. That is en plus 1, right? So essentially en plus 1 equals this times that. Okay, so that means that's going to be times en minus 1. Okay, that means I can put these together, which basically gives me en plus 1 equals, the first term is 1 by f prime r times the second term is minus 1 by 2 f prime r times en times en minus 1. Now, what is this quantity? This quantity is en plus 1 equals minus 1 by 2 f double prime r by f prime r times en times en minus 1. Now, if you recall, we got exactly the same expression in the Newton's method as well. right? We said in the neighborhood of the root, this quantity can be shown to be some, let us say, C delta, and this is less than 1, okay? This is less than 1, in which case we said the error is primarily controlled by these two factors, okay? That means we can say that En plus 1 equals some in the vicinity of root En times En minus 1, which is basically less than 1 quantity here that is being multiplied here, okay? Now again, after all this algebra, what we got is this factor which is basically multiplying that is simply something that is less than 1. That means the error is not going to grow because of this factor. Rather, it is going to be controlled with the error of the previous iteration and the error of the current iteration, right? That's all it is. But then, unfortunately, we don't have an expression relating n plus 1 to purely in terms of n or n minus 1. We have again as a product of n and n minus 1. So now I have to assume some behavior for the error so that I can solve for how does En plus 1 vary as a function of En, right? If this is the case, then I can say when I go from n to n plus 1, this is how my error is going to increase or decrease. But then now it is as a product of n and n minus 1 error, so I cannot directly tell from here. Rather, I can assume that my error at n plus 1, let us say modulus of error. I'm not really worried about whether it is positive or negative. Error it can be both, but error is going to can grow in the positive direction or negative direction. Let us say this goes as some constant k times e of n to the power alpha. That means I'm assuming that my En plus 1 goes as some constant times. That means the error at n plus 1 will be error at previous iteration to the power raised to the power something times k. I think this is a appropriate assumption, because if alpha turns out to be 1, that means the error increases or decreases or at the same value as previous, and if alpha turns out to be less than 1, it decreases with that particular rate, and so on, right? So I'm assuming this thing. Then similarly, I can also assume that En goes as k times inspired by the by the same equation I have. En goes as En minus 1 to the power alpha, right? If this is the case, I can write for error at n minus 1 from the above equation as goes as error at n divided by k to the power 1 by alpha, right? I simply wrote an expression for modulus of En minus 1, okay? That means now I have expressions for En plus 1 in terms of En, and then En minus 1 in terms of En. Then I can go back to this equation, substitute for them. On the left hand side where there is En plus 1, I can say k times mod En to the power alpha equals some C delta times En to the power 1, and then En minus 1 is, this doesn't look to be minus 1, okay? En minus 1 to be mod En to the power 1 by alpha divided by k to the power 1 by alpha. So then what I have is, if I send k times mod En to the power alpha equals C delta divided by k to the power 1 by alpha En modulus to the power, I have 1 plus 1 by alpha. I have 1 here, 1 by alpha here, so I can combine them. Then this is the, on the left hand side. So this is the expression I have for Ens, right? So on both sides, I can compare the exponents, or compare the exponents, essentially equate the exponents, right? Because these are equal, so the exponent should be equal, right? So equating the exponents of En on both sides, right? Because this is given as equal. So that's going to be alpha equals 1 plus 1 by alpha. That means alpha plus 1 by alpha equals alpha. That's going to be alpha equals, what we have is alpha plus 1 by alpha, which is basically going to give me alpha square minus alpha minus 1 equal to 0. That's going to give me alpha equals roots of the quadratic equation minus b plus or minus square root of b square minus 4ac by 2a. Okay, that's going to be 1 plus or minus square root of 5 by 2. This will come out to be approximately alpha equals 1.62. Okay, if you take the positive root. Okay, so that means alpha value comes out to be somewhere between 1 and 2. That means En plus 1 goes as k to the power En to the power 1.62. That means it is better than linear right? It is not linear convergence, but it is not as good as the Newton's method, right? So this is still better than bisection method, right? Because in bisection method, En plus 1 equals 1 by 2 En, whereas in Newton's method, En plus 1 equals En square, right? It was decaying with that thing, better than bisection, but not so much as Newton's method. Okay, but it is still super linear convergence, better than linear. So super linear convergence is expected for secant method in the neighborhood of the root. Okay. Now I have one question. So, I mean, essentially, what we have done in this secant method is simply we have replaced how we calculated the derivative, right? I mean, f prime of xn is all what we have replaced, right? If we had used f prime of xn in the Newton's method, we said we are not going to use this. Rather, we are not going to use the analytical expression, but we are going to use this in a numerical value, right? In a numerical derivative is what we want to use. So this is the numerical derivative. But then why did the convergence change? It was 2 here. Why did it drop to 1.62 instead of 2? Can somebody say why it has dropped? Any idea what it could be because of, any comments, anybody?
Sir, is this related to that exponent comparison step where we are comparing the exponents, but the coefficients may not be the same?
No, no. Exponent comparison is fine. I mean, from exponent comparison only we're getting 1.62. But why did it drop? I mean, all we have changed is the way derivative is calculated. Instead of using a analytical derivative, we are calculating using the secant formula, right? My understanding is that it is to do with the approximation of a secant, right? Instead of using tangent, we are using secant. We are saying that this tangent has the same slope as the secant. I think that is the reason why the convergence has changed, because we are not exactly giving the tangent as the expression. I think that is the reason. Maybe you can figure out again, if there is a better answer why this is different, although we have only changed the derivative. Okay. Fine. Any questions so far? Yeah. Any questions, anybody? No? Okay. Fine. So with this we finished the secant method as well. So we looked at the bisection method, we looked at the Newton's method, and then the secant method. Yeah. So in the secant method also we have written the pseudocode, did a sample program, sample hand calculation, and then we looked at the convergence analysis. Okay. So we have done all these three. Similar to the Newton's method, but secant method also can be used in conjunction with the bisection method. That means you can run several steps of bisection method, and then you can switch to secant method, okay, to get higher order convergence towards the root. Okay, fine. So next what comes up is solution to system of nonlinear algebraic equations. But before doing that, I want to take some time. As somebody asked yesterday, I kind of ended up coding a little bit of programs in MATLAB for your help. To help you. So I'm going to show you those programs and then discuss some nuances of this MATLAB programming so that you can get better at it and then work on your assignments easily. Okay. So I'm going to share the entire scheme. Let me share the screen. Okay. Now, do you see the MATLAB console?
Yes, sir.
Yes, sir.
Okay. Is this okay, or should I make it bigger? This is the font okay? Are you able to see?
This is
Yes,
this
sir.
is
This
okay,
is
sir.
okay.
This is okay.
This is fine. Okay. One second, if I can able to. Okay, fine. So okay, so luckily this is fine. Okay, so then what I have here is Control S. Okay, so what I have here is just a simple inner product, like the way we have done before. Inner product is basically take two vectors and then multiply component by component and then sum them, right? Essentially, you have A dot B. That means you're going to run A1 B1 plus A2 B2 plus A3 B3 until n, and then this sum is what is the inner product or dot product. Okay, so I named my file as inner product dot m. Okay, that is the name of the file, and I defined some function. Okay, now you may need to use some functions in MATLAB, because then your program will be what is called as a modular program, right? That means next time you want to call again, use the same functionality, you don't have to rewrite it again. So for example, this inner product I can call with any two vectors. I don't have to keep copying this set of statements wherever I need to calculate the dot product. Rather, I can just call it using inner product and then pass these values. So the syntax goes as function and then square brackets value equals name of the function, that is inner product. Okay, inner product times essentially the parenthesis, and then you have arguments. Arguments are n comma vector 1 comma vector 2. Now here inner product is the name of the function. I have now I named the name of the function and the name of the file to be the same. Now when you do this, you will be able to use this function anywhere in that folder from any other file. Okay, then if you use this function inner product in any other file in the same folder, then it is going to look for a file named inner product.m, and then it's going to look up this function from there. Okay, but then if you want to use the function within the same file itself, then you must rename the file to be different name than the name of the function. Okay, so in this case, I'm not going to use it in here. I'm going to use it somewhere else. As a result, I kind of wrote like this. Okay, fine. For example, let us say I'll come down. Okay, so okay, let us say there is value. So input arguments are n comma vector 1 comma vector 2. N is the length of the array. Vector 1, vector 2 are the two vectors that I want to take dot product of. And then this value is basically need not be value. It can be it is basically all the output arguments. Let us say value 1, value 2. I want to pass so many arguments, then I want to return so many arguments, then I will basically add more arguments here. But in this case, I just have to return only one value, so it is value 1. Okay, and then value, just value. Now that value is what we have to populate in the program, so that when we are done, that value is returned by the function. Okay, now this is that means anything that you want to return from the function after it finishes, you have to put it on the left hand side. Function square brackets, you have to write it there. Now this behavior is very different from what you observe in C or Fortran. In C, you can return values, but in C you can only return one value, or you cannot return multiple values in C. If you want to return multiple values, then they must be passed as arguments to on the right hand side. That means you will put more arguments here, and some of them can be input arguments, some of them can be output arguments. Okay, but this behavior is different compared to C. In MATLAB, you can return more than one value, but all of them will be returned in the same order you have written here. Okay, now this behavior is also related to something known as pass by value and pass by reference. So in C, you are always concerned with pass by value and pass by reference. That means if you pass, let's say, vector 1, in C there is a way by which, if it is a pass by value, vector 1 will be passed by value. That means whatever you have called with that value, it is going to make a copy of that and it's going to use it in this function. That means when you go back to the previous function, the place where the function was called from, that value is going to be different, because if it is a pass by value. But if you have pass by reference, that means if you pass the address and you're going to change it, then it is going to not make a local copy in the function. Rather, it is going to work with the same vector that exists in the previous program. As a result, when the function has finished and returned, the value that you are referring to in the main program has now changed because it has passed by reference. Okay, we don't have to worry too much about this thing, but then in MATLAB, it is always passed by value. That means it's going to make a copy of that and it's going to use it. So as a result, anyway, so whatever change we make here can be returned through the output arguments. So it doesn't matter whether it is passed by value or passed by reference, except that passed by value is actually going to consume a little more memory, because whatever vectors you have, whatever matrices you have, it's going to make more and more copies of that. Okay. Anyway, we are not very much concerned about it at the moment for this course. So I initialize value equal to 0. Then I run a for loop for I equals 1 to n. Okay. And then value equals value plus vector 1 times I times vector 2 times I. So that means I'm going to sum all these things. Okay, is what I do. Now, of course, I could do this. Let me uncomment these things. Okay. So let me uncomment this. Oops. I could not do it this way. Okay, let me delete. Okay, so there must be some block delete as well. Okay, so this is now saved, but then I try to run it. Let's say you click on this run button. It says function name must be different from the script name. Now, this is happening because I'm trying to call the function name as the script name. So let me change it to some dot product. Okay. That is my function name. My script name is inner product. So let me call this as dot product. So we should be able to make sense out of the errors that it throws. Then only we'll be able to kind of, and then I'm essentially defined n equals 5, array 1 equals some values, array 2 equals some values. Then I'm saying result. So this result is like my value equals dot product. So dot product function, after it returns, this is going to go there. And then I'm calling the arguments are 5 numbers are there, array 1 and array 2. Then I'm going to just print display a result. Okay. So let's now try to run this thing. Okay. It has done. Inner product is called, and then it says result equals some 1.0028 into 10 power 5. That's what I have obtained. Okay. So it is able to run because of this change. Okay. Now again, if I were to call it, let us say from here, this is a similar array operations that I have given to you before. Okay, in which case I have used dot product as a variable here, but with a capital P. So here I have used inner product. So now if I try to run this thing, it is not going to run because it's going to give an error, right? So as a function is not supported because I have modified this function. So I should basically, I can either, I have to now change it to inner product. And then I have to comment this guy. Okay, comment all this, and oops. Okay, I think this thing. Okay, this is a command forward. Okay, command forward. Okay, so that's done. And then this is uncomment, option comment. Okay, so now this is commented, but then my function is there. So now I can run this thing, and then command shift. This is run. Okay, now you can see it has run, and it has printed two values, 1.0028 in 10 power 5, which is coming from this dot product. The other one is coming from this result, which is called from the inner product. Inner product is this function. Again, these two are in the same folder. Okay, so we need not worry about them as such. Okay, the names are different. Okay, any questions on this? Is it clear, this part of using some functions and then running them? And then the for loop syntax is for I equals 1 colon n. That means this is starting, this is the ending, and then you give a tab and you write, and then you say end for ending the for loop. Similarly, function value in square brackets, you give whatever you want, the output arguments, and then when you're done with defining the function, you say end. Okay, end, it can end the for loop, end can end the if conditions, and can also end the function. Okay, so we just need to be a little careful. Okay, questions on this? Is this part clear, how to use now in MATLAB? If you don't put these semicolons at the end, then what is going to happen? It's going to essentially print everything. Okay, I think this is not a nice idea because now I have again the dot product. Okay, so let me go here and then run this thing. Okay, with the inner product. So it is basically going to print all the values, right? So it's printing all the values, which is when it calls it calls them, so it will print every evaluation of the every value. See, it is printing value equal to 0. So it's printing C value equal to so much, value equal to so much, and so on. That's because it starts with 0 and then it keeps printing all the things. If you put a semicolon, all this output will be suppressed. Okay. That means if you want to debug, don't put a semicolon. It's going to print step by step what is the values it is doing. But then again, it is not a good idea because it's going to put every possible variable, everything that it has evaluated. But that may be very difficult for you to decipher. But then you can be clever and then only do not put semicolons for those statements where you want it to print to debug, and then you can again suppress them with a semicolon. Okay, that is possible. Okay, questions on this? Questions, anybody? Is it clear?
No, sir. Yeah, at this time it is clear.
Clear?
Yes, sir. Yeah.
Okay, fine. So no questions. Just give me 1 minute.
Okay.
So then I have also ended up writing this bisection method that we have discussed, and also wrote a pseudocode. So I basically wrote a bisection method code for you. So what we have is now in this bisection underscore method dot m, I defined a function. This function is basically my f of x. So I say function, and then as I click on function, you see that it is being underlined and end. That means it is checking for function is followed by end. That is the extent of the function. And then square brackets value is the value it's going to return. Okay, and equals fn of x. That means it's going to take one argument, that is x, and it's going to evaluate this. Whenever I want to evaluate this function, I'm going to call it as fn with some arguments. Okay, then value equals x is the argument. So this is going to be x cube. This is exactly the same example that we have done in the class by hand calculation. So we have x cube minus 3x plus 1. Okay, I have another function which I'll test it later. Then I have defined this function. Okay, so from here to here is my definition of the function. Okay, so that is the definition of the function. That is done. Then I have another function. Another function is basically my bisection method. Okay, so I'm defining something called function. Again, it is giving the result. Result is going to be the final root of this function after solving for bisection. So then this function name is bisection, and as we have discussed, I wrote bisection A, B, that is the initial guess A, initial guess B, n max is the number of iterations we want to do, epsilon is the tolerance. Okay, then now from here on, the steps are exactly same as what we have wrote in the class. So f of a equals, f of a is the function value at a, it's going to be fn of a. That means when I write this fn, I'm actually calling this function fn. Okay, it's calling this function. Now see how easy it is when we use functions, right? If I have not used it, here I have to write a cube minus 3x, 3a plus 1, right? And here I have to write b cube minus 3b plus 1. And if I have to do it several times, I have to basically keep on doing this with different values. And more importantly, let's say tomorrow I want to give another function instead of this thing, then I have to go to each and every line of this thing and then change everything. Instead, now I just have to change this function, or maybe call or define another function fn1, with a different function arguments, with a function this thing expression, and then that's going to basically use that function instead of this, and as a result I'm going to make lesser mistakes. Okay, so it is always a good idea. I think some of you are already into programming and software and so on, so you know that reusing the code is very important. You should not be like keep on writing blocks and lines of thousands of lines of code where most of the code is actually a repeat with a small changes. Okay, that is not a nice practice. So you should be able to reuse the block, reuse the code, reuse the functions, and all these things. That means if I write a function, I should be able to give it to you and you should be able to use it. Okay, that is how the idea is, which will basically reduce the amount of effort required, and also it will reduce the number of mistakes and bugs in the code, okay, in the program. So I have f of a equals fn of a. Similarly, f of b equals fn of b. Now, what is a and b? A and b is something whatever I will pass later through when I call this bisection. Okay, those are my a and b. For those values, it's going to evaluate the function a and function b. Now, if fa star fb comes out to be greater than 0, that means their product, that means both are positive or both are negative, in which case their product is always positive, then we are not interested in this range because this range has no change of sign. That means there is no root in this range. That means we say that function has the same value at both at both. Now you see, I'm instead of using display, I'm using fprintf. So display is basically simply displays the value of the variable that you have given, whereas fprintf is a better function. In C, you would have called it as printf. In Fortran, in MATLAB, you call it as fprintf. Okay, that is a formatted printf, and fprintf is going to the format is exactly same as in C. So you wrote in double quotes. You say that function has the same value at both. You use %f to print floating point numbers. You use %d to print integers. Okay, so we want floating point numbers. So I say %f and %f, double quotes close, and then comma a comma b. A comma b or whatever the values. Okay, so when you put on this thing, it also shows you help fprintf format specifier comma a1 comma a2. Okay, fine. Then once you are done with this thing, there is nothing else to be done. So then return and then end. This end is closing for the if. Then you calculate error. Error equals absolute of b minus a. Okay. Then we start the iterations. Iteration is for I equals 1 colon n max, and then there is a corresponding end for this. Okay, for this for. So that will be there. Then first thing we do is calculate the midpoint value. That is c equals half of a times a plus b. That means 0.5 times a plus b is c. Then once you have c, I can calculate what is f of c. That is, again, I call the function for that midpoint, that is fc. Then if this error which I have just obtained here is going to be less than epsilon, that is the tolerance, then I'm going to print it as fprintf. Okay, solution converged in %d iteration. So I'm going to print what is the I. It converged in, let us say, 20 iterations, 50 iterations, like that. Then I'm also going to print the solution is such and such. Okay, c is the root, that is the solution, and then I'm going to say result equals c, because I should put this thing. If I don't put this thing, then my result will not be populated. That means result is going to have a value of 0 or something, which is never updated. So my c value is lost in the function. So when I come out, I will never get the value of the c. Okay, so I'm equating result equals c. Then I say return. Okay, go back to the calling function. Then you say end. That ends this if condition. Then now if, let us say, now this is basically calculation of c and fc. Now if fa star fc is less than 0, that means a and c are having opposite signs, then we don't want b. That means b should be removed, or b should be updated, or b should be updated with c. That means my new b is going to be value of c, and then fb is going to be fc. Okay, I am again not calling f of function of c or function of b here, because that is redundant. I mean, that is kind of time consuming, right? Because I have already calculated this thing. The function value is available in fa, fb, fc, so I just can directly assign it rather than recalling the function. Okay, similarly, if else, that means if fa star fc is not less than 0, it is greater than 0. That means if it is greater than 0, that means my a and c have both the signs. So I don't want to keep a then, right? I want to replace a with c. That means a equals c and fa equals fc. That's what I want to do. And then end. Okay, that finishes the if else end block. That is done. Then we again recalculate error. This is absolute of b minus a. We are doing this thing because the previously we have calculated error outside this for loop. Okay, we have calculated here. So that's why we are redoing it inside the loop for every iteration. So we do that, and then we say fprintf, and then \t, %f, \t. So \t basically means it gives you a tab in printing, and then \n will give you a new line, so that all these values will be printed one after the other. Okay, and then you have c comma fc. That means at every iteration I am printing what is the c value, midpoint value, and the function value, and then I say end. Okay, so that is the this end is for the for loop that we have written. Okay, it is for this for loop. This is for this for loop, and then once you're done with this thing, again I have to say result equals c, because I did not say this before. I have set this result equal to c only inside the first if condition, where if my only if it has converged, only then I have set this thing. So let us say if in the number of max iterations I have given, the program may not converge, in which case I may never enter this error will not be less than epsilon. As a result, I will not enter this thing, but I still am interested in seeing what is the result. Okay, if that is the case, I'm going to populate this result equals c, and then I'm going to end it. Okay, so that is my bisection method. Okay, now this is bisection method. Okay, now I am calling. So because I'm calling all these functions within the same program, I'm calling my program name as bisection underscore method, whereas my function as bisection. Okay. Otherwise, you know that if you want to use it in another function, then you have to name the function name and the file name to be the same, so that MATLAB will be able to look it up. And then all these files should be within the same folder. If they are not in the same folder, then you have to add path such that MATLAB can go and check all those paths where these files can be found. And inside those files, these functions can be found. Okay, if you make use of a function that is in a file that is not in that folder. Okay, fine. So then I'm calling this thing, I'm calling root is the return value. I'm calling bisection, method function with 0 as my A, 1 as B, and then 50 is 50 iterations. And I say 1A minus 4, that is 0.0001 is my tolerance. Okay, with that I'm calling it. Then I'm going to say fprintf, the value of the root is such and such, and it has converged. Okay, fine. Then I'm going to go ahead and run this. Okay, now you see it has printed something. Let me see if I can make it maximize. Okay, so it has printed bisection method. First one is 0 and 1. This thing is 0.5, right? It had the function value. Then 0.25 function value and so on. And it has already become 0.000144. After this, it would be less than this value. So its solution is converged in 15 iterations, and it basically prints all this. Okay, so that's what it has printed. Okay, now let us say I can, of course, increase. Let us say we might be interested in knowing what is the how many iterations also, which iteration has what value. Then I can even put this thing and then say this is my I value and so on, and I can run this. Okay, now you see that 14 iterations, every iteration value it has printed, and then the 15th iteration you have it is converged. Okay, fine. Now let me say instead of 1e minus 4, let me say 1e minus 6. And I want to go to even finer value. So 0.347351, I'm not very satisfied because our 347321 still it has an error of 1e minus 4. That's why I want to go finer. So save and then run. Okay, so it has converged in 21 iterations. That is nice. So again, it went to 0.247296. Okay, so you can keep on doing this thing. If you want even smaller, can do that. I think hopefully it will converge 27. So it is unable to print it here because I have given %f. So you have to probably give %lf. That is going to be the long floating point. Okay, hopefully it has printed. No, it is not printing in a nice way. Okay, fine. We will, or maybe double or something. I have to see if, yeah, why it is not printing. Maybe I have to change it. We can learn that later. Okay, I have to also look it up. Fine. So we can do it like that. Now let me give. Let me say I want to modify this function for another. This program for another function. That means I don't want to work with this function. Okay, I want to work with this function. That is x cube plus x power 5 plus x cube plus 3 is my function. So I just can simply change that one. Then I have to also change what are the initial arguments I give. That is for bisection method. Let me say I give you minus 1.5, minus 1, 50, and 1a minus 4. Okay, I give this thing and then run. So this is now a new function. Okay, it has converged. This is exactly the same function we have used in maybe in the Newton's method or something. Okay, so it is doing minus 1.25, minus 2, and so on. It has converged to 1a minus 4 in 14 iterations. The value is minus 1.10536. Okay. Now let me say I know that the root is between minus 1 and minus 1.5, but I give 1 and minus 1. Okay, it says function has the same value at both 1 and minus 1. Output argand result. Okay, so that means so it is saying it has the function value same, so it cannot proceed. It returned, but then it is giving an error because the output argument result was not populated. So I can go back and say, if this is the case, I can say result equals 0.0, right? And then put a column, semicolon. Okay, save it and then run. Okay, now there is no error, right? Because the function has the same value and the value of the root is 0. So the value of the root is 0, but this is not correct. So you need to give more diagnostic messages saying that the root is not correct, right? Otherwise, people may think 0 is the root, okay? But 0 is not the root. I just wanted to fill it up here, okay? Fine. Any questions so far on this thing? Hopefully, this will help you get started. If you want, I'll give you, I've already given you array operations, hello.m matrix operations, and inner product I'll give you, and then bisection method also I'll give you so that you can play around with it. And then with that help, you'll be able to write, next set of programs. Yeah, you can also easily look up how to make a graph for, an array. I think if you just do a small search, you'll be able to get that. I have not covered that part in here. If you want, I can look it up and give you as well. Okay. Any questions so far on the MATLAB part?
No, sir. We'll review and get back to you, sir.
Sure, sure. I hope this is helpful so that you can, kind of get started with programming. Okay. If anybody else has any question, you can ask me, or else we can proceed. Okay, fine. So let's get back after the MATLAB session. Let's get back to where we were. So we finished the. Okay, so we finished the. Okay, so I don't know why it is so thick. Anyway. So we finished the, okay, so it's now better. Okay, so we finished the solution to system of nonlinear equations. Sorry, we finished solution to nonlinear equation solutions, right? Now we have to look at solution to system of nonlinear algebraic equations. That means till now we were only looking at one function f of x equal to 0, which is non-linear, and that solution we have found as whatever is x equal to something, right? But then now we are looking at a system of those nonlinear equations, okay, with nonlinear algebraic equations. And again, these are pretty common. You're going to get them in when you work with CAD or in design software and so on, where you have to find intersections of different curves. So you're going to find these things there in the designing, designing, modeling and stuff like that. And you're also going to get these nonlinear algebraic equations in several chemical reactions, okay, and many other applications. In fact, the the fluid flow equations are nonlinear, but they are not algebraic equations. They are nonlinear partial differential equations. For example, if you want to use, let's say, the GPS, which you every day use on your phone, the global positioning system, you basically your phone is solving a system of nonlinear equations. Every time you look up for a cab or something or on a map, then you're essentially making your phone solve a system of nonlinear equations, okay, to exactly locate you where you are on Earth. It is solving a system of nonlinear algebraic equations, okay. We'll probably look at this example a little later. So there are, again, several other examples and there are several other uses of systems of, you will encounter these systems of nonlinear equations very often in engineering and in science applications. So again, the solution methodology is basically a straightforward extension of the Newton's method. Okay. So in the Newton's method, what was the idea? The idea was that you have a nonlinear function. You had a nonlinear function. What we said was we have linearized this function, right? How did we linearize this function? We said the tangent to the function is a good approximation. That means the tangent itself is a linear function. And then with the tangent, we found a root, and then we repeated, right? And from the new root, because we are solving for a tangent rather than a nonlinear function, this root is not exactly the correct root. So we have to go to the next, again, evaluate the function and then draw a tangent and then repeat and so on, right? So we kind of repeat it until and hope that under favorable conditions, this has converged to a root of the function itself. Now, in solving systems of nonlinear algebraic equations as well, we're going to linearize all the functions, okay? And then apply something like Newton's method. Okay, we're going to essentially iterate again, but then this time we are iterating to find all the roots, not just one root. I mean, essentially you have root that is coming from several variables, right? Several variables together will constitute a root, which will satisfy all the functions at the same time, okay? Now, of course, you can also extend secant method to finding solution to system of nonlinear algebraic equations, but that will be a little more complicated than the Newton's method. But nonetheless, the concept is the same. We're going to linearize and then repeat and then find the root, okay? So that is the idea. So we will go into the method maybe in the next lecture. So for today, I'm going to stop here because we are out of time. If you have any questions, please feel free to ask me. Otherwise, we'll again meet on Monday at 4 o'clock, okay, to continue with our discussion on nonlinear solution to system of nonlinear algebraic equations.
Sir, am I audible?
Yes, yes.
Just in the interest of understanding it, if there is a mind map between multiple methods and how it is getting, connected and how the steps are happening, that mind map would help if it is available, or how we can make the mind map.
What is
maybe you can just suggest us.
Oh,
Yeah,
between the different methods, is it? Yes, you are.
Yeah, as a mind map between in the same method as well as between methods, how it is connecting, what we are finally going towards, and maybe it's just for me to understand. I'm just asking, maybe not for maybe others might be having it as a better understanding. It's just from my perspective.
Okay. No, I mean, essentially the concept is straightforward. I mean, you have some nonlinear function, right? You have some nonlinear function. In bisection method, you are essentially trying to, in all the methods, you're trying to get to this root, right? So in bisection method, you start with, let us say, two initial guesses. Initial guess 1 could be here, 2 could be here, and then you are essentially saying, I'm going to look at the half of this value, and then from the half, you're going to identify which half the root is going to lie based on the sign of the functions, and then in that half, you are going to again make the midpoint, and so on, right? That is how the bisection method is progressing. Whereas in the Newton's method, you are drawing a tangent. You're drawing a tangent and then saying that, okay, this is my tangent, which is an approximation to the nonlinear function. But if I had to calculate the root of the nonlinear function, that is here. But because I have drawn only a tangent, this value I would get is not the root. Rather, I have to repeat it again repeatedly and then calculate the root again, right? So that is what we are doing in the Newton's method. In the secant method, we are saying is that instead of drawing this tangent, we are drawing a secant. That means I'll give you two values, and then you're drawing a secant, and then you're saying where will it cut, and from there you draw one more, and then you draw another secant, and so on. Right? That is how the secant method is working. Maybe if you do a little bit of review of what we have done, look back at the notes, you should be able to figure out what is it. I mean, otherwise, if you have a specific question, come back to me again. Okay.
Got it, sir. Thanks for this overview.
Yeah. No problem. Yeah.
Sir, regarding assignment, actually, I was trying the assignment problem 1 on the MATLAB, sir, to cross-verify the code.
Okay.
Okay, and what
Okay.
I was seeing was with assignment problem 1 without round off, if we do with only pivoting the first line, we were able to get the solution in a manual method. Because when we pivoted the first line, the second line automatically the coefficient was becoming 0, and with that we don't need to pivot the second line. That was happening.
No, but if you use MATLAB, but the 4-point arithmetic will not be respected. It will it'll do with much more accuracy.
Sure, sir. Sure. Actually,
Yeah, but if you do hand calculation, it should be possible.
Yes, sir. Actually, my question is, sir, like if for a certain matrix, if second line pivoting, if it's not required based on the matrix condition, how do we take that in MATLAB coding, sir? How do we see if should we look for every time on this?
No, so essentially what you should do is, if you want to code it up, then let us say if the second pivot becomes 0.
Yes, sir.
Yeah, if it becomes 0, then you cannot operate with this thing. That means you have to look for a non-zero value below that row and then do exchange of rows, right?
Yes, sir. Okay.
Yeah. So it means what you can do is you can push this row. So you can identify another non-zero row, where the value is non-zero, and then you can push this entire row there and then bring it the other one here, because that means this is already, if you bring this up, then this row is already has a 0 here, which you wanted to make in the next step.
Yes, sir.
So that you can do.
So by we have to write a command to rearrange in every.
You have to correct. So you have to copy all these row values into some buffer, and then copy these values here, and then use that buffer to again copy it here.
Okay, sir. Okay.
Some kind of swap you have to do. But I suppose it will not become 0. I think you will get something like 0.0001, something like that.
Actually, I was checking without round off, sir. With round off, 0.0001 is coming.
Okay, fine. Yeah,
round
okay.
off, it is going to 0.
Sure. Yeah, without round off, it is fine. Yeah, without round off, it will become 0. I think that's what even. Yeah, fine. I just want to make sure that you are not getting an incorrect answer as such. Okay. Fine. With round off, you'll get 0.0001. It will give you incorrect result. When you do pivoting, you are actually going to get correct result.
Yes, sir.
Sure. Okay, thank you. Yeah. Okay, any other questions, anybody? Okay, if not, I'm going to stop here, and then we will meet on Monday again. All right. Okay, thank you, guys.
Thank you, sir.
Yes, sir.
Thank you.
Thank you, sir.
Thank you. Bye. Thank you.
Thank you, sir.
Thank you.